Okay, so what I've done is, this is the board I started last time. I added the stress-based approach as well. So now for this unique problem, we have everything on the board. In both approaches, the major condition, equilibrium or compatibility, that comes naturally along with the particular solution approach. The rest is similar. There's a traction-free condition associated with boundary conditions, and the rest based on static equivalence you post-process for the torque or the twist. Okay? So we have everything on the board. And what I'd like to do now is solve a particular problem. And that's going to be part 3 as an application of these ideas. And that's going to be an elliptical cross-section. And our cross-section is like this. Let me remind you what the coordinates are. Always, I'm looking from the front. So left is x2, upwards is x1, and out of plane it's x3. Okay. And that is our domain S. The boundary is del S. Eventually, if we have to do an arc length parametrization, the arc length parametrization goes counterclockwise. And the major axis I will call B, and the minor axis I will call, minor radius I will call A. Okay. And now I'm going to proceed with the displacement pace approach. Okay, so the first solution method. Now, we have two conditions that the warping function has to satisfy, equilibrium and the traction-free condition. Now, ideally, those are the conditions from which you solve towards your function, right? But both for the displacement and the stress-based approach, in this particular case, I think I've done something similar, well, actually, at least partially similar before. I'm not going to solve for those equations directly. I'm going to assume the simplest possible form that could possibly do something, and I'm going to show you that it works, okay? So the simplest possible, the warping function that it turns out you can work with in this particular case. So actually, this is not it yet. Let me write. So what I'm doing is I'm putting a constant, okay? We know that a constant just induces, first of all, a displacement along the x3 direction. It's arbitrary. I could pick it to be anything. In fact, I'll pick it to be 0. And then I pick linear terms. And then you will see that since this is arbitrary, I'll pick it to be 0. And then, due to the specific requirements, B and C turn out to be 0. So if I just put this simplest thing, that's not a constant, it doesn't work. So I'm going to add just one more term. The simplest possible next term is dx1, dx2. And this is not trivial. It will make some contribution. It turns out this alone does work. So the argument is that this one is irrelevant to me. And I'm going to cross over the other two constants, B and C, at this stage. I have not shown you that they vanish, but they will vanish. And this actually is the form that I will be dealing with. But let me show you why they vanish and why this is therefore the simplest possible choice. Okay, and that's the key word. Right, so you have everything summarized on the board that I just went over a minute ago. The equilibrium is Laplacian psi is equal to 0. And it's a, this is called a bilinear function. So you have at most order 1 appearance in both coordinates. So the fact that there is x1 multiplying x2 does not destroy it. It's not linear, it's bilinear. So such a function, Laplacian is equal to 0. So that's identically satisfied. I do not have to worry about it. But let's look at the traction-free condition. The traction-free condition is the tricky thing, usually in the displacement-based approach, whereas compatibility is the tricky thing in the stress-based approach. So the traction-free condition, I'm just writing exactly what we have derived without any modification, has to be equal to 0 on del S. And this one, it's not trivial. I will plug in everything. We have to enforce this. So let's work with it. So psi comma 1, right? A I already got rid of, and it doesn't contribute anyway. So it's B plus dx2. And c comma 2 is c plus dx1, right? So this whole thing I could write as follows, right? I'm just going to pull a DDS outside. And so it's DDS. There is a x2 here, and there is a constant here. So if I write here bx2, the derivative of that is b times dx2 ds is that term. And likewise, I can combine the remaining terms. If I write d minus 1 x2 squared over 2, the derivative of that will be the whole first term. And then I could work with the second term. Likewise, I can have a minus cx1 here and minus d plus 1 x1 squared over 2. So that has to be equal to 0. Okay, so since you are perhaps still writing, I'm going to pull this board down. Continue up here. So whatever is, so DDS of something is equal to 0, so that thing has to be a constant, and let me call that constant 0. And I'm just rearranging and putting term that multiplies x1 first, and then there is a term that multiplies x2, and I multiplied everything by 2 just for convenience before I introduce the constant. So x1 squared plus d minus 1 x2 squared. Okay, that's equivalent to what I just wrote in the previous board. Okay. So E is a constant that I don't know yet, right? That's an extra constant. Now, what I'm going to do is I'm going to look at a number of points. And so this is a requirement that is supposed to hold on the boundary of the elliptical domain. So I will pick just judiciously, actually not so arbitrarily, points on the boundary. So for instance, I will look at that point. It has coordinates a0. This one has coordinates 0b, etc. And I will look at their symmetries as well, minus a0, minus 0, minus b as well. So first, let me look at a0 and minus a0. Okay? At those 2 points, this has to hold. So because I picked 0, x2 vanishes, minus 2c a minus d plus 1 a squared has to equal to E. And here as well, plus 2ca minus d plus 1 a squared has to be equal to E. And therefore, you see 2 things. One, you subtract this from that, everything cancels. 4ca is equal to 0. So this is a capital C, by the way. Right? So C has to be equal to 0. Okay. I got rid of this one constant. And moreover, since C is equal to 0, you could go into either equality is the same. We find that E is actually equal to minus d plus 1 a squared. So I found what this constant E is, and I also found out that C is actually 0. That was the term that multiplied x2. So similarly, you can look at two other points, 0b and 0 minus b. And let me just quickly work that out as well. So we have 2b small b, and for the lower one, that's a plus, this is a minus, and plus d minus 1 b squared is equal to E, which I'm now making use of from the first set of points. I know what E is, so E squared. Okay. And here you observe that B is equal to 0 by subtracting two equations. And that's not the only thing. Now I have from either equation this equals that, and therefore A and B are just geometrical parameters. I actually can determine what D is. So if you go ahead and solve for D, you will find that it's equal to B squared minus A squared over B squared plus A squared. So if B is larger than A, it's a positive constant. And therefore, I know what the warping function is. The warping function is equal to, right? So now, this has happened actually several times before when I was working with the air stress function and integrating towards displacements or at other portions of the course. I always wanted to make the minimal, put the minimal, let me say, inside, just the crucial ones. Of course, an insightful mechanician, one who has experience, would omit these terms from the outset. But I just wanted to show you that this is indeed the simplest possible ones, and these ones, even if you include them, they vanish, right? So that's what we have shown, and therefore C is equal to dx1, x2, and I found out what D is, and it's equal to, therefore, B squared minus A squared, B squared plus A squared, x1, x2. Okay. And we are done with the major part of the displacement-based approach. So now, if I have a circular cross-section, I know that when I torque it, plane sections do remain plane, and therefore they do not warp, which means that Psi should be equal to 0. And indeed, if it's a circular cross-section, B is equal to A, Psi is equal to 0, as it should be. Okay? So we've covered the circular cross-section demonstration on the fly. Okay? Now, to proceed and make a link between the twist per unit length and the torque, we have to calculate the torsion constant, right? And let me also do that. So I'm just going to write here what J tilde was defined to be. It was R squared, or x1 squared plus x2 squared. And if the warping function is not equal to 0, and it's not presently, an additional contribution. So the function is fairly easy, dx1, dx2. D I already have determined, so this is dx1, this is dx2. You can plug in and integrate towards J tilde. So I'm just skipping a few steps here. You can fill in the blanks, and you can show that the result is equal to pi a cubed, b cubed over a squared plus b squared. So in these integrals, eventually right here, x1 squared and x2 squared coming up. x1 squared, apart from a constant, x1 squared dA has to do with moment of inertia about 1. x2 squared about, actually the other way around, x1 squared I2, moment of inertia about x2 axis. x1 squared, moment of inertia about one axis. And eventually, those you can get from tables what they are, and therefore evaluate the integral towards this, right? You don't have to really carry out an explicit integral over the ellipse. All right, so now that is the result, and I'm just going to write it also in a slightly different way that serves the purpose of interpreting this result. And so what I've done is I've arranged it in such a way that there is one term that multiplies the polar moment of inertia, and the polar moment of inertia is, I'm not going to evaluate it, we just recall what it is, J is equal to R squared dA. Well, in fact, I do have the answer here. Let me write that. For an ellipse, it's equal to pi AB, A squared plus B squared over 4. Now, what does J tilde serve? J tilde allows us to determine that the twist per unit length for a given torque is equal to T over mu J tilde. So once I know it, the torque is prescribed, I can find alpha or vice versa. Now, if we look at this term, right, and if we just actually recall what A minus B squared is, it's A squared plus B squared minus 2AB. Of course, it's greater than or equal to 0, right? So A squared, therefore, is always greater than 2AB. And therefore, this term is always less than or equal to 1. In other words, J tilde is always less than or equal to J. Okay? So what does that mean? Now, suppose I said, okay, maybe warping is not so important. Let me omit it. Even for the elliptical cross-section, I'm going to assume that plane sections remain plane. That's essentially saying that psi is equal to 0. When psi is equal to 0, instead of J tilde, I get J. And if I try to calculate the twist per unit length, let me call it alpha 0, calculated under the assumption that psi is equal to 0, it's going to be T over mu J. Okay? Now, this equation is exact if it were a circular cross-section, but presently, it's not going to be a faithful representation of the physics because J tilde is less than J, and therefore, the real alpha is actually not equal, greater than or equal to alpha 0. Okay? So you would be underestimating the twist per unit length, hence the deformation of the structure. Okay. And depending on the geometry, the difference can be significant. Okay. It's not an error that you would like to be making. All right, so that is a very quick demonstration of the displacement-based approach. And now I'm going to go to the stress-based approach, and then I will have a numerical solution for this particular problem. Okay, questions over here? All right, so. So now, just like we did for the displacement-based problem, again, we could have gone ahead, and the requirements are on the board. We have to solve this partial differential equation subject to this requirement. Okay. Now, instead of solving them directly, I'm going to work backwards and assume the simplest possible form for phi. And it turns out the simplest possible form for the area stress function is this. So the idea is you start in by throwing a constant. Is the constant important? In this case, it is. You will see. And then you can throw in bilinear terms, a term that multiplies x1, a term that multiplies x2, a term that multiplies x1 and x2. And then if you pick points judiciously again, you will see that all of them, one by one, vanish. And because they vanish and you're left with now only c, it's not sufficient. And then you throw in the next set of complicated terms. You already made use of x1 and x2, so you go to x1 squared and x2 squared. So that's the way the procedure works. You assume something, Does it work? Well, it doesn't. It dies away. So you throw in the next set of terms. This is the simplest possible thing that eventually works. So in this case, I'm not going to show you how those bilinear terms would vanish, but I encourage you to go ahead and put them in and see that they actually do. So in this case, equilibrium is already satisfied. We have to look at compatibility. And compatibility says that Laplacian of phi is a constant, and that constant happens to be 2 mu alpha. Now, the Laplacian of phi, that is straightforward, is simply 2a plus 2b, right? And therefore, from this, we find that, well, a and b are constants I have to determine, so I have to write one in terms of the other. I'm going to write b in terms of a, so it's equal to minus a minus mu alpha. So now I'm left with only one constant to determine. And maybe I'll work eventually on a different board. Once I find a, and you plug in a in here, the form that you will find for b is this. Okay? I'm just making a note at this stage, but I still have to show you what a is. Okay, so I made use of the compatibility requirement. I have to go to the traction-free condition. Now, the traction-free condition is very simple. It's just phi is equal to 0 on the boundary. Okay, so I just have to pick points and make sure that it is actually satisfied. So I'm going to pick 2 points. A point along the minor and another on the major axis. So now, phi is ax1 squared plus bx2 squared plus c. So the constant now goes into that condition. It is important. It's not arbitrary. So it's a squared. B has no contribution in this point. Plus c is equal to 0. And in this case, b squared plus c has to be equal to 0. And therefore, from the first one, c is equal to minus a squared. And I had already found out that b is equal to minus a minus mu alpha. And therefore, from this equality, by also now making use of c, right? You plug in c in here, you plug the form of b from the compatibility requirement, you have only a single equation in terms of a, and you find what a is. Okay? A is equal to minus mu alpha b squared over a squared plus b squared. And now once you find a, you can go back and evaluate b, and likewise you can, I have already written that result. Let me write down the result for c. It's mu alpha a squared b squared over a squared plus b squared. And we are done. Okay. I have determined what the Prandtl stress function is. So to summarize, after a little bit of arrangement, putting everything together, that's the Prandtl stress function. Now you will notice, of course, that the quantity in the brackets, if it's equal to 0, that describes the equation of an ellipse. So, which means that, right, contours of constant phi, have the shape of an ellipse. That's what it means. And moreover, we see that x1, x2 equals 0, that's the center of the cross section. So minus, minus, it is a positive quantity. And on the boundary, because this is the ellipse equation, it's equal to 0. And therefore, phi is equal to 0 on the boundary, as it should be, because that's the condition that I impose as a traction-free boundary condition. So on the inside, it's positive, and towards the boundaries of the ellipse, phi decreases. Let's just keep that in mind. Okay? But there's a lot of information essentially there. So I'm going to go ahead and also calculate the torsion. Or the torque T is equal to 2 integral phi dA. I'm not going to just crunch through the math. You will find that it's equal to that quantity. And in fact, as it should be, this is exactly equal to J tilde, the torsion constant. So eventually, you are solving the same problem. It's just through a different approach. What comes out should be the same, irrespective of whether you're pursuing a displacement or a stress-based approach. So one way or the other, you find that T is mu alpha J tilde. OK. Now, there is just 2 more things that I'd like to show. At this stage, we're done with most of the solution associated with the stress-based approach. There is the displacement remaining, so I need to work back towards the warping function to complete if this was my approach. And also, I'm going to make a note of one more thing, the traction on the cross-section. So let's first get the warping function out of the way. Okay? So last step of a displacement-based approach, of a stress-based approach, we work towards the displacements. And the only tricky thing here is the out-of-plane distortion. So we've already written the equations, psi, 1 and psi, 2. They had these forms. Let me just remind you. I'm just rewriting exactly the same thing. And now you can go ahead and plug in phi. Phi has a very simple form, and therefore the result is something quite simple. Okay. So, comma 1, I integrate, right? There will be a x1 coming here and possibly a function of x2. But that function here could at most be a function of x1 as I integrate to 2. And therefore, that additional constant that comes in is not really a function. It is a constant. And that constant goes into psi. It describes an arbitrary displacement in the axial direction, which I have omitted already in my previous displacement-based solution. So therefore, I'm just going to say that psi is equal to the core term, which is x1, x2. Okay. And hence, we recover exactly the same warping function, of course, as we should. Now, okay, the last piece of information that I'd like to share. If the cross-section was circular, okay, and I put a torque here. In ME231, we had derived that you can look at any any circle at a position r from the from this centroid, and the shear stress, okay, is tangent to that line, and we at that point said that it's a tau, and tau is of course a constant in that case, and it's equal to Tr over J, where J is the polar moment of inertia. We all remember that. Okay. Now let's go to this setting. I'd like to look at the traction. Now, this present setting is a little bit more complicated because what characterizes the in-plane geometry is not just a radial position, it is x1 and x2 together, right? So it will have two components, and we already wrote what it is actually. And so T3 is the traction on the plane with normal 3. I have written what it is. It's simply sigma E3. Now I know the form of sigma, and therefore it's equal to simply sigma 3 E1 plus sigma 3 to E2, and sigma 3 1 is phi comma 2. Sigma 3 2 is minus phi comma 1. And therefore, this is equal to phi comma 2 E1 minus phi comma 1 E2. When we were trying to develop the tangent and normal to this boundary, we already worked on a similar form. Now I look here, this is phi comma 2 minus phi comma 1. The components of the gradient of phi is phi comma 1, phi comma 2. This has the components reversed with a minus sign. So this is exactly equal to, as we observed earlier for tangent and normal, it's grad phi cross product E3. Okay? So that's the form of this expression. It's another way to write exactly the same thing. That's nothing new. Now I think about what gradient of phi is. Now gradient of phi is something that points normal to, you will remember from your math course, gradient of phi is a vector that is normal to lines of constant phi. Okay? And so it's going to be normal to the lines of constant phi. And lines of constant phi, I know the contours of constant line are of an elliptical shape because of the form of the Prandtl stress function. I've just told you that, right? So it's going to be normal. In which direction? In the direction of increasing phi. And phi is maximum in the middle, 0 on the boundary. So it's going to point inwards. So inwards cross E3 at any point, right? Inwards cross E3 is going to be equal to a vector that is tangent, first of all, and also tangent in the counterclockwise direction. So this must be T, the traction on the plane with normal 3. And why is it in that direction? Well, no wonder, because that's the direction that I'm torquing in. That's the way the traction has to develop. So when you look at this picture and that picture, they are, in some sense, quite similar. Now, let me work it out a little bit further. And I want to calculate the magnitude of the traction vector so that I can find the equation that is quite similar to the circular one. So if you eventually, right, go ahead and plug in the form of phi, right here, that's the traction, calculate the magnitude, and you will find, okay, it's just a few lines. You will find that that is mu alpha r tilde, and I know the relation between mu alpha and t, right? So mu alpha is t over j tilde. So this is nothing but t r tilde over j tilde. Now j tilde, we know what it is. It's the torsion constant. R tilde is just a quantity that I have defined here for convenience, it's not a very clean expression, but it is an expression that is convenient to introduce, so that the equation for the magnitude of the traction, TR tilde over J tilde, is equal or similar to the expression that we had for a circular cross-section. And moreover, if I have a circular cross-section, then A is equal to B, and you will see that R tilde is exactly equal to R, J tilde is exactly equal to J, and therefore you recover the same equation, right? So the pictures are quite similar, right? With perhaps one difference. On these lines, the torque is the magnitude of the traction is a constant for a circular cross-section. R tilde is not really a constant on that cross-section, but oh, I suppose not. Okay. But anyway, so the pictures are very, very similar. Okay, and that's it, actually, for the stress-based solution approach. And that pretty much concludes all the numerical, analytical developments that we have made. So at times, the course was almost like an ordinary differential or partial differential equation course, but I hope I was able to walk you through those difficulties as cleanly as possible. So the last thing I'd like to do, as I have always done, is give you a numerical demonstration of this problem. Okay? And the numerical demonstration, also I will enjoy showing you some pictures based on the original work of Saint-Venant, who worked on this problem first, right? So now Saint-Venant I have worked on this a lot, so now I managed it. Okay, so Saint-Venant, let me open up the computer, worked on this problem or published this problem in 1855, okay, more than 150 years ago. Now, is that too old? Well, I mean, so electromagnetic theory is not too much younger. Quantum mechanics is a tiny bit younger. It's at least 100 years old. So, I mean, I don't really care how old it is. 150, it's not actually too old for such a fundamental problem, okay? And so Saint-Venant worked on this problem, and he published a paper in the Academy of Science, French Academy of Science. And I found that paper for you. And as soon as this thing warms up, I'm going to show you what it is. And so in that paper, of course, he works out all the mechanics, but there are also beautiful sketches of how things warp. And I don't know if Saint-Venant himself has drawn those sketches, but somebody has, and they are very nice. So this is the paper, right? Torsion of prisms, and by Saint-Venant, okay? So, and the date should be written somewhere here in Latin, 1855, right? I'm sorry, in Roman numerals. So in that paper, page 144, I believe, there is the sketch of the torsion of an elliptical cross-section. It's not a very clean sketch, so I found a slightly cleaner one, okay? And that's the setup. So he doesn't have any prescribed boundary condition. He's assuming somehow an ideal case where you can apply torque in both ends. Or you're looking at a portion with the end condition at least, if you like. And this is the front view, right? So you see that when you torque, plane sections do not remain plane. Looking from above, it's like an infinite sine. And looking from front, these dark shades indicate outwards, and the light ones indicate inwards displacement. Okay, so that is 1855. So so this is certainly not a small deformation example, right? The twist is exactly through an angle of 180 degrees, right? If you fix that end and rotate 180 degrees. But it's not small deformation. And at Saint-Venant's time, certainly nonlinear continuum mechanics had not matured yet. And certainly there was no suitable finite element, a nonlinear finite element framework. So from that respect, this thing is really beautiful. They must have done an experiment, of course. But what I've done is now I've constructed the same thing numerically. And that's the setup, Saint-Venant's setup. And we can, in this case, it's not a small deformation computation. So it's a nonlinear framework, and I have to choose a nonlinear elasticity model. I picked NeoHook, okay? And that is one among many nonlinear models, nonlinear elasticity models. I picked it because the only thing you need to describe it is a Young's modulus and a Poisson ratio. And then you have it. So then I torque through 180 degrees, right? So compare that with this beautiful sketch, right? So you wonder, I mean, those people were really, really brilliant. So now the thing we'd like to look at here perhaps more closely, right? Red indicates so the colors indicate displacement along the x3 direction, which is the x3, this axial direction. This is x1, this is x2, as I had in all of my sketches as well, right? So when you look from above, right, again, you see something like their sketches, right? I'm sorry, like an infinity sign here. That's what you have here as well, right? So it's a very, very faithful representation. But this is large deformation. I cannot compare it with our analytical solution. So I'm going to go ahead and open the model that corresponds to the small deformation setting. Okay? So now, this is the setup, and this is the solution. I'm going to show you only one solution. So what I've done here is, this is a problem where displacements are very, very well defined, right? So what I've done is I fixed this end, okay? And I twist it through an angle of 10 degrees. It's not really a very small, actually, deformation. It's not very small. But what I've done is I prescribed this rotation, prescribed it not exactly through cosines and thetas, but exactly in the form. If we could get a shot here, just to remind you, I prescribed those displacements like this, so assuming that they have the form of small deformation. If you do that, the match is better. Okay? So this is U1 and U2, describes the in-plane motion, are described through those equations at the free end. There is no restriction on the U3 displacement, and therefore it's free to warp. At this end, it's completely fixed. Now, the thing is, of course, it will try to warp there as well. It tries to warp everywhere. And you see the displacement U3, right? Outwards, blue, inwards, yellowish, or right, yellowish, it's nothing in the middle. It tries to warp here, but it's constrained, and therefore there will be an end effect. And again, we recall Timoshenko is a beautiful solution where he shows that this warping develops with an exponential decay from this fixed constraints. Again, it's an end condition that decays exponentially. And here, actually, you already see here, if you just omit this tiny portion, the picture looks the same all across the axial position. Okay, so that's the setup that I described. If I want to omit that end condition, what I could do is, as I've done for the contact problem, I could have imposed the exact warping here as well as a boundary condition in the 3 direction, and that way I could have, so U1 and U2 do not change because it doesn't rotate, but for U3, I could have imposed the same exact solution, and that would be a perfect solution everywhere. But I wanted to show you the end condition. So let me come to that. It's always important when it is relevant. This is the sigma 3,3. Right? As we have argued all throughout, it is 0, except for the end condition. Okay? So our assumptions are very, very reasonable. Now, I want to also show you what the displacement is. And what I'm doing here is I'm going to take a cross-section, a plane. Okay? So I want to look from the front, and I'm going to take that plane very close to this edge and very close to here. Here it's free to warp, here it's not. Okay? And what I will do on that plane, right? So this is x2, that's x1 direction, and out of plane is just a way to indicate the magnitude of displacement in the 3rd direction. So first of all, it has warped. You see that it has warped. The plane itself, the color plane, indicates the numerical solution. These lines of contours is just a way to superimpose the analytical prediction. The analytical prediction is full warping, and it's the same, of course, everywhere. So it doesn't match, of course, the numerical one because of the AND condition. I just wanted to show you that they do not necessarily match if the AND condition prevails. Likewise, you can look at the magnitude of the traction, right? It looks like this, almost following the contours of the ellipse, but not quite, but it has the shape of the ellipse almost. So the surface is the numerical, the contours are the analytical one, right? So again, near the end, they do not match because of the constraints. So now what I will do is I will go ahead and take that cut, not at 0.05 times L. The length, by the way, is 1. The minor and major radii are 0.1 and 0.2. So they're actually pretty large, but still the solution is quite nice. I'm just going to modify the point of the cut plane, and I need to do a small adjustment. Okay. So now I'm at the freely warping end. Displacement, warping of numerical, analytical, perfect match, right? And you can look at also the traction, perfect match. Okay. So the analytical solution is actually working beautifully. Okay. So that is pretty much the demonstration of the Seminow theory. And I hope you have enjoyed the ride, and that concludes actually the course. Okay. So thank you for listening.